So you can put it here.
Oh, you're smart. I don't know whether should we start. But we'll go on.
All right, cool. So good morning, everybody. My name is Drew Branch.
I'm Billy McLaughlin.
And we are here giving a presentation on mobile application reverse engineering under the hood. So I'm Drew Branch. I'm an associate security analyst at Independent Security Evaluators. I have my BS in electrical and in computer engineering, and I'm currently pursuing my master's in cybersecurity at UMBC. And I love to learn about new tech and also playing various sports.
I'm Billy. I'm also an associate analyst at Independent Security Evaluators. I have my BS in computer science and computer security, working on my master's. It's taking a little while. My hobbies are like hacking around on new stuff, play a lot of video games, play some soccer.
So a little bit about ISC. It's a boutique security firm that specializes in assessments and also evaluations of our clients' environment. We focus on application assessments, I guess geared towards like more so of like the white box perspective. We take the approach of like knowing how, I guess, a hacker would think, and we also think like hackers to perform our assessments so we can, I guess, get in-depth familiarity with our application and also like attack the application as a hacker would.
We do a lot of different types of assessments. Clearly we do mobile stuff. We do a lot of web apps. We do some native stuff, and basically we're all over the place. So it's a great place to work.
So the overview of the presentation, we're going to be looking at the common security mistakes that devs usually make within mobile applications. And then we will, I guess, describe the problems that we encounter during these assessments. These problems are real world problems. And then we're going to be showing you guys how to overcome these problems and then touch on reverse engineering techniques.
So for the iOS half, Drew's going to be handling that. He's going to be using Damn Vulnerable iOS app to show some things. For the Android half, I'll be handling. I wrote a small custom application that we'll be looking at.
Yeah, so a little bit about the Damn Vulnerable iOS application. It was developed for pen testers such as yourself to learn new skills and also test your previously known knowledge. So let's hop right into it. Developers tend to store sensitive data on the file system. Example of this is like credit card information, username and passwords, and also other personal information. Oh, sorry about that. This type of information should not be stored on the file system. We feel that other information may be stored, but we don't feel like it's necessary. So a couple problems, or a problem that we run into while checking is that mobile application or a mobile operating system does not include file browser capability built in. So how do we overcome this? For iOS, we use an application called iExplorer. It's a free Windows and Mac OS application. You just download it and you can just run it on your computer. Many of its features you can run and use without having to jailbreak your iOS device. So such as extracting files and also opening various files such as databases, plist files, and also just, I guess, regular files such as images and also documents. Okay, so within Damn Vulnerable iOS application, they have a module where you can store various types of information in various file types. So here, as you can see, I am storing test user as the username and also secret password as the password. Now to your right, you see I have iExplorer open and I have the iOS device connected to my laptop via USB. And as you can see here, you see the damn vulnerable iOS application folder, and I have the documents, and the user info.playlist file is within that folder, and you can easily just right click and then open that file. And within that file, you can see that secret password is stored and test user is also stored. Now, this process usually takes about, I want to say, a minute to about 2 minutes, because you have to, open up various files and see if the developer actually stores sensitive information in files. But this process is fairly simple, it's easy, and we actually encounter this quite often during our assessments. So another common security mistake is sending sensitive data over an unencrypted HTTPS connection, such as user credentials, credit card information, and also other sensitive information. Now, it is inappropriate to send this type of data without any encryption, such as using SSL TLS, or just using, I guess a commonly used encryption algorithm such as AES to encrypt your data before sending it to the server. Now, a problem that we encounter while checking this is that we cannot run a packet sniffer on the actual mobile device. So what can we do? We can run a proxy server on another system, such as a laptop or just a regular computer system. And for assessments that I complete, I tend to use Burp Suite. Burp Suite is a very handy tool. So for this example, the damn vulnerable iOS application has a module that you can send, I guess, credit card information over, HTTP connection or request. For this example, I am sending 1 through 9 twice as my credit card information. I know it's larger than 16 digits, but oh well. Also, I am sending 1, 2, 3 as the CVV number, and fake name as the name. So here is the packet that was captured by Burp Suite. As you can see here, you can see the type of request it was, which is a post. And also at the bottom, you can see the fake name, the CVV number, and also the credit card number here. So another common security mistake that developers make is they don't, I guess, really test for security bugs within the server's API. A couple examples are missing authentication in RESTful APIs, also broken authentication checks, and sending sensitive data to the server. Now, a problem that we encounter when we're testing for this is that if they're using HTTPS and check and search properly, we cannot perform a man-in-the-middle attack. And I guess mobile devices, they don't have like built-in developer tools like browsers do. So developers, I guess, tend to overlook, I guess, easy problems that can easily be fixed. And they also, I guess, think that obscurity is, I guess, a good, I guess, method of security to secure this type of information from reversing and also testing an API. So how do we overcome this? We will use the, interception software such as Burp Suite. Within iOS, iOS has a list of trusted CAs within its operating system. We can easily have Burp Suite create his own CA and then upload that into a mobile operating system and have that CA be trusted. Now, Burp Suite, if you aren't familiar with it, is a Java application that can be expandable using various plugins. It has various features such as the proxy, spider for like I guess web app crawling, scanner which scans web applications for I guess commonly known vulnerabilities, and also like a repeater for manipulation of various requests, and you can also resend requests. It has like a couple other features that you guys should check out and use. It's pretty handy. So problems while checking, I guess, security bugs in an API is that the application might use its own CA or have the CA built into the application. If a developer is actually building the CA into the application, they're using a process called cert pinning, which is just associating a host with its expected cert or public key. So to overcome this, there's a tool. You can find it out on the web. It's called SSL kill switch. It attaches to the application and suppresses the typical implementations of cert pinning. And this application requires the iPhone to be or iOS device to be jailbroken. So I'm gonna take a quick detour. Kind of like this picture. The detour won't be as crazy as this, but so jailbreaking, what is it? It's the exploitation of security bugs within the operating system. This allows, I guess, the user to have super user control over the mobile application, or the mobile operating system. And it also allows users to install various applications that are not within the App Store. So a couple developer misunderstandings is that developers tend to, I guess, overestimate the difficulty of jailbreaking a device. It's very simple. There are applications out there. It makes the process straightforward. Also, they underestimate the types of attacks that you can perform without jailbreaking the device, such as opening files and extracting data that way. Now, it should be mentioned that I guess conventional laptops are already in a jailbroken state. So I guess when a developer says that if a user has to jailbreak a device, then the severity of, I guess, this attack will be really less than what it really is. But jailbreaking, the process is so easy that mostly all users can, execute this process and have user control over the mobile operating system. Jailbreaking also allows users to remote into iOS devices via OpenSSH, and also install various pen testing tools. So like I said before, there are one-click jailbreak applications out there. Right now, there are jailbreaking applications for mobile devices running iOS 8.4 and lower. I would tell you guys to be careful when upgrading your iOS device, because you might not have a jailbreaking application available for 1 to 2 weeks or even up to a month after release. So let's go back. So storing sensitive information in the keychain. Developers, I guess, have this notion that the keychain is 100% completely secure and that any information stored in the keychain cannot be accessed. Developers usually store passwords or encryption, decryption keys, and also, I guess, auth tokens and various other sensitive information that they feel the need to store. So problems while checking. We can't see the keychain without jailbreaking the device. So to execute, I guess, to access the keychain, we will have to jailbreak the device. And there is a program out there that we can use to do so, which is called keychain number. Now, the iOS security model relies on the fact that a user does not have, root access to the device. So if we can upload, an application to the mobile operating system, then we can actually dump the keychain. And Apple is like being, contingent on users not being able to do this. So storing sensitive information in the keychain. For this example, we're going to be using the damn vulnerable iOS application. There's a module within it where I will be storing, this is a secret within the keychain. So after we download and transfer the keychain dumper to the mobile operating system, we can, set its execution rights and then execute the program. And keychain dumper dumps all the data that is stored within the keychain, such as any information that app developers wants to actually store in a keychain, and also any other information such as Wi-Fi passwords, stuff like that. So as you can see here, to your right, we see the damn vulnerable iOS application entry in the keychain, and you can see this is a secret. Is clearly displayed in plain text. Another, security mistake that developers make is hard coding sensitive data in the application binary, such as passwords, decryption keys, and also like client-side authentication and session management. Developers think that mobile applications are harder to analyze. A couple, problems that we run into while we're trying to analyze the application binary is that applications from the App Store are in fact encrypted by default. So when an application is encrypted, we cannot, load the application binary within IDA Pro, which is just a disassembler, and view the actual, the assembly code that makes up the program. So what we have to do, we have to jailbreak the device and then run an application called Clutch. Clutch is an application that decrypts the application's binary, which allows us to extract the binary and then load the binary within IDA to analyze it. So let's take another detour. So like I said, binaries from the App Store are encrypted. They do not contain any debugging info, which is helpful for reverse engineers. A binary from the developer, they are unencrypted. They contain debugging info and is a preferred method when completing an assessment on a mobile application. It's kind of like, white box versus black box, if you want to think of it that way. All right, let's go back. All right, so now I'm going to be touching on reverse engineering techniques. So I use a dynamic analysis tool called Snoopit. It's a very useful tool. This is the easy way to perform dynamic analysis. You would have to jailbreak the application and then add Snoopit to Cydia's source list. Cydia is automatically installed when you jailbreak the iOS device, so you don't have to worry about installing Cydia. So what Snoopit does, it actually watches out for common events that are important to reverse engineers, such as keychain access, file system access, as well as network activity and also cryptography activity. It has various other features, but I tend to use it just for these 4 core items. So I'm going to show you guys an example of Snoopit here. I have a screenshot. It is actually analyzing a program here, and as you can see that I have the keychain tab open, and you should be able to see that You can see when the keychain was read, when the keychain was written to, and also when the entry was deleted or updated. Now, Snoopit is a web interface, so you will need, I guess, a laptop or a computer to access it. And it's like an easy, user-friendly application that makes dynamic analysis so much easier. So extracting implementation details. iOS applications are coded in Objective-C. Objective-C compilers are different than I guess C++ compilers. Objective-C uses message passing and late binding, which leads to the inclusion of embedded strings, class information, methods, and also global variable names. Now, message passing, is when objects are sending each other messages. Late binding allows classes to handle the same messages like in a different manner than other classes. So how do you extract the implementation details? There's an application called ClassDump. You would have to download this application and then upload it. Well, you can either extract the binary and have it on your computer system and I guess view the details that way, or you can actually put ClassDump on the mobile operating system and run the ClassDump on the binary like that. Now, ClassDump displays all the classes, the methods and variables, and also properties associated with those classes, and the user-friendly, easy-to-read, I guess, layout. Okay, so some, I guess, advanced dynamic analysis techniques. Recent versions of iOS require LLDB as the debugger instead of GDB. LLDB is or was created by Apple, and it is a remote debugger configuration. Sorry, it requires a Mac and an Xcode. So, to use LLDB, pen testers must extract the iOS developer image, the debug server. I'm sorry, from the developer image. Add the correct entitlements to allow the program to debug other applications, and also load it onto the iOS operating system. So the usage, you would have to SSH into the mobile device via OpenSSH. So you will have the application running. You will need the process ID. So here, I am searching for the damn vulnerable iOS application. I see that the process ID is 368. So then I will run the debug server to accept all communications or connections on port 1234, and I am attaching to the process 368. So after that process is attached to and stopped, then you would go to your host machine. You would open a terminal and type in LLDB. If you do not have the Xcode command line tools, a prompt will prompt you and ask you if you want to download and install them. You would click OK. Excuse me. And then after that, you would type in platform select remote iOS. It will load the various libraries that are required. And then you would type in process connect to the IP address of the mobile device, and also the port number you specified in the previous screen. So here's a tool summary of the tools that I mentioned during this talk. Each of these tools are readily available on the internet, and they provide various documentation on these applications. Really good. Alright, so this is iOS.
All right, so again, I'm Billy McLaughlin. I'm going to be talking about the Android side of our talk. Why did that just... All right, sorry, brought up the other one. All right, sorry. So today, we're going to be talking about assessing Android applications. Specifically, I'm going to be touching on network traffic, encryption, decompilation, some source code analysis, and debugging. I was just off by a slide. Apologies. So I want to talk about a couple terms that you might not be familiar with that are required for this. An APK is an Android package file. It's basically the equivalent of a Windows MSI or a Debian Deb file, basically just an installer. It contains everything that's required for the application to run. DEX stands for Dalvik Executable. You can think of it as the Android equivalent of a Java class file, basically. The DVM is the Dalvik virtual machine. Again, it can be thought of as the Android equivalent of the Java virtual machine. ART, I'm not really going to be talking about much, but in recent versions of Android, it has begun to replace the Dalvik virtual machine. So, what is this? What are we looking at? I've developed a simple online storage application for this talk. This is what the login screen looks like. Very simple. What can it do? All right. So our goal for this section is to enumerate the functionality of this application. To do that, we're going to be tapping around on the application. The software required is just going to be the app itself. Hardware required, fingers. So it can allow users to log in. It can allow users to download files. It can store files locally, as we can see from this LS on the Android device. And finally, it can decrypt files in-app. So basically the idea is you can download encrypted files. They can then be viewed in the app. Very simple. So now we can start to formulate a plan. So we have some targets. We want to look at storage methods. We want to look at how it's downloading things. We want to look at the encryption. So the first big question is the storage secure? Our goal here is to investigate the files that are stored on the SD card, downloaded through the app. To do this, we're going to pull the files off of the Android device so we can check them out in a friendlier environment. Software we're going to be talking about is going to be ADB, which is the Android debug bridge. It's a command line utility that can be used to interact with an Android emulator or a physical device running Android. So you can send commands, you can push files to the device, you can pull files, a whole bunch of stuff. You can execute commands on it. I'm going to be using a couple Linux utilities. Three I'm going to touch on are file, strings, and less. I'll talk about them when I get there. All right, so first up, we want to see what is being stored by this application. So this application stores files on the SD card in a directory called private things. So what this command is going to do, it's going to use ADB, the debug bridge, and we're going to pass the shell command to it. So basically what ADB shell does by itself is it will give you a shell on the device. If you pass more parameters, as I have, it will actually execute that command on the device and print the output directly to your screen. So what this is going to do, it's going to give a long listing of all the files in the directory /SD card /private things. Everything in the app writes to the SD card. So we do that, and we can see one file. When we were enumerating before, I mentioned you could download files. We would have downloaded this file. That's why it is currently on the SD card. So now we want to get that file onto our desktop so we can do some poking at it, see what it looks like. So right now, empty directory on my host machine. And then what we're going to do next is going to invoke ADB pull, which will download a file from the device to the host machine, specifying the file. So /SD card /private things /1, which is the file we were just looking at before. All right, took about a third of a second. And now if we do another ls, we can see we have the file on our local machine. So now we do stuff with it. First thing I want to do is run the file command. File command, very simple. Basically, it attempts to tell you what type of data is stored in a given file. So in our case, file, the only parameter is going to be the location of our file, which is an Android SD card 1 on our host machine. So it turns out that when we run file, we don't get anything particularly useful. It tells us there's data in this file. All right, so it doesn't seem to be able to figure out anything beyond that. Okay, so we're going to try something else. We're going to try the strings command. What strings does is it will print it'll print text strings from within a binary file. So typically you want to run this on something to see, for example, you can run on an executable. You might be able to get some information about libraries that are being loaded because they'd be in plain text. So in our case, we're going to run it on our file and we get a bunch of nonsense. So again, this hasn't been particularly useful. This is truncated. There's many lines of this. Short strings that don't seem to mean anything. Okay. So next we're going to look at less. Less is a command, just what everyone's probably used if you're familiar with Linux. It's a pager that lets you look at the contents of a file. So we're going to run less on our file, and we get a bunch of garbage. So from doing security assessments, if I see something like this, chances are it's encrypted or encoded or something's going on. So the result of this is the file's not human readable. Didn't get us too much helpful information, but got us somewhere. So back to the question, is storage secure? Maybe. We don't know yet. So we're going to step off to the side, and we're going to look at these downloads. Our goal for this section is to gain access to restricted files, files we shouldn't be able to download. We were allowed to download one because we own that file. So now we're going to try to download something else. To do this, take a simple approach. We're going to guess URLs based on the one that was requested for the file we were allowed to download. To do this step, I'm going to be using Burp Suite. My co-presenter mentioned it. It's a very useful intercepting proxy. Has a lot of features. I'm going to be using a very small subset of those features. Basically, the application, Burp Suite's going to sit in between the application and the server that it's requesting the file from. So what I want to do is I want to capture the request on the way and change it to attempt to download a different file. So first off, this is what it looks like when we downloaded our file during the enumeration stages. So we have a host, which is the URL it's requesting, and the file name was 1. Very simple web server it looks like, right? Just an IP and a file. So the request we go through, we get a response, we get an HTTP 200, okay. And not surprisingly, the contents is a bunch of garbage. You'll see the content length is about 1 megabyte. Something to keep in mind. So let's try to get a different file. So this was the original request, the one that I just showed. But you'll notice that there is another tab now that says edit a request. That's because in transit, as the original request was captured, I edited it before forwarding it to the server. So I edited 1 to be 2. Figured it'd be a good idea. Something's called 1, chances are something else might be called 2. So I forward this request along to the server. I get a response. Again, I get a HTTP 200 OK. Now that's telling me that there is a file. It worked. I downloaded a file that, it's not mine. It's somebody's file. I probably shouldn't be able to download that. Again, a bunch of garbage. Probably the same type of garbage as my other file. You'll notice that the content length is also shorter on this file, so it's definitely not the same file with a different name for some reason. So it looks like it downloaded, but we want to make sure. So we're going to use ADB shell again to get a long listing of the files in the app directory on the SD card. You'll see now we have 2 files. So we definitely did download something that we probably shouldn't have been able to download. So the result of this section is pretty good. we found that there's some kind of broken authentication or no authentication when downloading files. Basically, any user can download any file. It results in a breach of authentication. It's a loss of confidentiality, and perhaps most important, it might result in possible changes to this app's development team. So real quick, let's talk about what we found out so far. We know that storage is possibly secure. And we know for sure that downloads aren't protected. So then we know that we can access the possibly encrypted files of other users. So now we want to know, are these files actually encrypted, or are they just garbage? So what we're going to do here is we're going to try to get a look at the source code of this application to determine that. To do this, we're going to be decompiling the Android APK. We're going to use a couple pieces of software to do this. ADB again, to pull the application off of the device. We're going to be using a program called dex2jar, which will convert dex files, the Dalvik executable files, into typical Java class files. So you end up with a jar file containing classes, rather than an APK. Wait. Yes. The first. I'll elaborate later. All right. And lastly, once we have that jar file, we're going to be decompiling that jar file with a Java decompiler. There's a couple around. There's JDGUI, Fernflower exists, Procyon. For the sake of this, I'm going to be using JDGUI. All right. So first step, we want to get the application off the device. So from my experience, I know that typically the APKs are going to be stored in /data/app on the Android device. So it's a simple pull, /data/app. I know the name of the app because I made it. So typically it's of this format. It's package com.derbyapp-1.apk. So for about half a second, now I have a copy of the application on my local machine. Cool. ls to verify, there it is. So now we're going to be using dex2jar to turn that APK into a jar file that we can then decompile. So I've copied in the dex2jar directory. It contains quite a few scripts. dex2jar has a bit of functionality that I'm not going to be using. So the command is going to look like this. I'm going to invoke the d2j dex2jar.sh script. It's going to output a file called dex2jar, same name, -dex2jar.jar. We can see it's right there. So dex2jar seemed to succeed. So our next step is to open this in a decompiler. So first step, you can see I added this new file here. Bottom right, it says jdgui100.jar. jdgui is going to be our decompiler we're using for this. So I'm going to launch it simply by using the Java command, passing the jar flag, or jar we want to run, and I'm passing our source code jar as a parameter. So this is going to launch the JDGUI GUI, and we'll be able to look at some of the code going on. So we see that this is what it looks like. On the left, we got a pane with classes. On the right, we have the code for the currently selected class. It's very useful, right, to be able to see the source code. Typically, I don't like to look at it in JDGUI, so I usually export the code to a zip file. All these decompilers have this functionality. Pretty useful. In the case of JDGUI, it's just file, save all sources, pick a location, save a zip. And then you'll see, now we have, bottom left, jar.source.zip. So this file is going to contain all the source for this application that JDGUI was able to decompile. So we need to unzip this using the simple unzip command quietly. The Q flag. Our new zip file specifying a destination to the source directory. So you see we have a source directory on the right, and just to make sure it's not empty, there's some stuff in it. So we're good. So now we have some source code that we can look at, right? So then the question is, are these files actually encrypted? Well, without diving in too deep, we can see a lot of imports from Spongy Castle, which is basically the Android implementation of Bouncy Castle. a very well-known crypto library for Java and C#. Also, judging from the class name crypto activity, it's probably pretty likely that there's some encryption going on. Looks like it. So the real question is the encryption strong? So our goal here is to investigate the encryption itself. To do this, it's going to require some source code analysis. We want to see what is actually happening. Myself personally, now that I've exported all the code, I usually use Vim, combination of Vim, text editor, ctags, which is it's a command that will generate an index file of all the objects found in like a source tree. And basically you can hop around between them. And AG and grep, which are just simple searching tools. So without going really into depth with this, don't have the time to do that, I will point out some of the code from an encryption function. So you can see they're using AES, CBC, PKCS7 padding, and they're passing this BC flag. So the BC is specifying the provider for this code, which is going to be Bouncy Castle. So we know that AES is strong when using CBC mode properly. PKCS7 padding doesn't have any issues yet. And further down, we'll see that the key is being generated as 256-bit. So without going too deep, it looks like this is pretty all right. Might be more efficient to peek around elsewhere than dive too deep into this. So, is the encryption strong? It looks like it is. Are we stuck? Nah, definitely not stuck. So our next question is going to be, can we get a key? Our goal here is going to be to grab this key out of runtime. To do this, we're going to be debugging a little bit. The software we're going to be using is ADB in conjunction with JDB, the Java debugger. So first, there's a little bit of setup. We're going to use a JDWP command in conjunction with ADB. JDWP stands for the Java Debug Wire Protocol. Basically, it's a way for the debugger to communicate with the virtual machine it's debugging. In the case of ADB, what this will do is list the PIDs, the process IDs of every running application that is currently debuggable. In our case, there's only one, my application, and this is its PID. Then we have to set up some forwarding. So basically, what this is going to do is we're going to be able to connect to our local port 7890, and that will allow us to communicate with PID 11129. So no output from that. Now that we have that forwarding set up, we can use JDB to connect, specifying a socket, to our local host 127.0.0.1 on port 7890. Once we do that, we are presented with a prompt. So that means that we're connected to the app, it's debugging in real time, we're good to go. For the sake of readability, clear the screen. So at this prompt, earlier, we were doing some source code analysis, right? We would have picked out some functions that look like they might be important. So within the crypto activity, there's an ENC function. Sounds like it would be an encryption function, right? So my idea is to break in that function and see what kind of information we can find. To do that in JDB, you use stop in, and you can specify a function or a line of code. So we got com.derbyapp, the package name, .crypto activity, current activity, .enc, which is the function. So breakpoint set, easy, right? In JDB, there's a command called locals. All right. So once we have that breakpoint set, we're going to have to use the app until that activity is invoked. So that has been done on the sides. So now JDB has a command called locals. It'll dump some of the local variables at the point where you've broken. So with the simple application, they didn't do too good a job. So when we dump the locals, we see that there's a seed variable. We see it dumps method arguments. There are none, but there are local variables. It's called seed, and this seed is a plain text string that says at least one uppercase, one lowercase, one number, and one special character, which is ironic because it doesn't have any numbers or special characters. So now that we have this seed, chances are we'll be able to break this encryption. Doing that is a little beyond the scope of this, but this is a huge part to moving forward. So the result of this is goodies. We have a seed. We can definitely proceed forward. What do we want to do now? Well, there's one thing we can do quickly, and that is test this new seed data with our downloaded file to see if the keys are shared. In the case here, that is the case. So the key is shared. We are now able to decrypt not only our own file, but remember that second file we downloaded you can now also decrypt that. Right, Drew? Yeah, that's nice of you to do that. So, that was encrypted. We did it. That's it. So that was a pretty simple sample, right? Typically, applications, not typically. Sometimes developers will do a lot better job. Sometimes they won't. This is a nice brief coverage of simple application. So what did we do today? We found an app, poked around at that app, found some target areas, downloads, storage, encryption. We investigated those areas throughout our talk. Found some issues, right? We found that we could download arbitrary files. There's a pretty weak seed going on. And then we chain those issues together to be able to break the protection mechanisms of the application. So that's the end of my talk. I want to thank all you guys for coming out, listening to us ramble this early in the morning. So I guess now we're going to open the floor to questions for both of us, iOS and Android.
Yeah. Richard.
So the question was, are iOS apps typically encrypted? Is that what you asked?
Android.
Oh, the Android apps. Sometimes developers will use obfuscation, but not like out of the market, no. Not like iOS.
Also, on the iOS side, what's the solution for, you're talking about the keychain, what's the solution for that? I guess developers generate encrypt stuff, put it in the keychain.
Yeah, so it was, question was the solution for, I guess, not storing sensitive data in a keychain?
Yeah, so what's the solution?
So, yeah. So, I guess information or sensitive information shouldn't be stored in a keychain. Usually, the approach to this will be to encrypt your data and, I guess, store it on a file system if need be, but you should stay far away from that as possible. Any other questions?
All right, thank you guys. If you have any other questions, you can come up to me.
Yeah, feel free.
I'll be around. Independent Security Evaluators is running a router competition in the Derby room, so I'll probably be in there at some point if you want to stop by. If you're interested in more Android stuff, my coworker Rick Ramgatti is giving a talk tomorrow with some GDB stuff and Ginny. So check that out if you're interested.
Yeah, we're over in the Derby room, right outside these doors here. Thanks.
Thank you, everyone.